Hello, everyone. So today we are going to actually launch into the substance of our course. And the first thing we'll get into is a discussion about various definitions regarding exposures and exposure assessment, and then also discuss human exposure distributions. So in the first section, we are going to talk about some exposure definitions. So before we launch into the discussion of formal definitions, it is useful to consider the context in which exposure assessment is done, whether in an occupational setting or an environmental setting. So in this course, which is about risk management, I'm going to be using the occupational setting as an example, but we should always keep in mind that the concepts can be applied to any kind of environmental setting. So I want you all to always keep in mind that the occupational setting is just an example to clarify things, but we can always extend it to other settings as well. So let's consider the occupational setting. Here I'm showing a figure with three rectangles. So in the top part of the rectangle, it describes the occupational setting, and there are three boxes in there. So the first box says it's the work environment that has contaminant generation sources. So in this work environment, the contaminant gets dispersed in the work environment by means of air movement in the factory floor, for example, or some other mechanism. But since we are going to be primarily focusing on airborne contaminants, let's just think that the contaminant is being dispersed via air. And in this environment, workers are moving around and near and far away from the contaminant generation source. And maybe they are doing activities that may be themselves generating contaminants. So it's a very complex environment in which there is spatial and temporal variability in the exposure. In the bottom part of the figure, there are two rectangles, and the job of the industrial hygienist or the job of an exposure assessor is to estimate the exposure of workers quantitatively. That's the focus of this course. So we want to estimate quantitatively the exposure of workers, or if you're looking at some other setting, the exposure of human beings in whatever environmental setting we are interested in. So on the right side of the box is the context in which such exposures are used in occupational epidemiological studies. And the epidemiologist looks at the health effects of these exposures on the workers and finds a relationship between the dose to the worker and whatever the health response might be. On the left-hand side of the figure, there's another rectangle, and that is, in fact, the primary focus of this course. And here we are looking at the management of exposure to the workers by the exposure assessor or the industrial hygienist if you're looking at occupational settings. And here the industrial hygienist or the exposure assessor comes up with an estimate of the worker's exposure and compares it to an exposure limit, a limit that says, okay, if the exposures are below this limit, then the workers are more or less safe. But if the exposures exceed this exposure limit, then some action needs to be taken. So on the basis of this comparison of the exposure estimate and the exposure limit, the industrial hygienist says, so everything is fine. The exposures are below the exposure limit. And so I'll come back maybe after some period of time, maybe a few months, I'll do another reassessment. So there's a periodic reassessment of exposures. If the exposure exceeds the exposure limit, then the exposure assessor or the risk manager needs to implement some measures to control the exposures and bring them down so that the exposures are once again below the exposure limit. And the third case, which is in the middle, is the exposure comparison is not possible with the currently available information, which means that you need to go and collect more information, which will make a decision possible. And so, as I said before, the occupational setting is just an example, and we can apply this very same framework to a general environment. And so here, as you can see, I replaced the word occupational environment with the general environment everywhere. And instead of exposure of workers, I replace it with exposure of regular people. And instead of occupational exposure limits, I'm just talking about exposure limits. And this is just to emphasize the idea that this is a very general framework in which we can consider exposure assessment. So, in the context of occupational exposure assessment, how does an exposure assessor or risk manager or industrial hygienist operate? So, the first thing that he or she would do is to conduct a basic characterization of the workplace processes. And by this, I mean that the industrial hygienist tries to understand what is going on in the workplace. What are the different industrial processes going on? What are the different chemicals being used? If it's a chemical manufacturing plant, for example, what are the available control measures to manage the workers' exposure? So, is there a good ventilation system, for example? Are there good manufacturing practices in place? Are the workers well trained in their job and be able to manage their own exposures sufficiently so that they are not exposed to unduly high levels? The industrial hygienist also tries to understand the workers' tasks. So, for example, if a worker is mixing two chemicals, what are those two chemicals? How is the mixing occurring? So, is it occurring on a regular table, or is it under a ventilation hood, or is it in a totally contained glove box type of a setting? And then finally, the exposure assessor needs to understand the contaminant properties. So again, looking at airborne contaminants, is it a gas or a vapor or a airborne dust? And is it a volatile chemical or not so volatile, semi-volatile or non-volatile chemical? Because all of these properties will affect the worker's risk of being exposed to the harmful contaminants. Based on this basic characterization, the workers are then divided into several groups that are called as similar exposure groups. And what this means is, so let's say you have a very complex workplace, and so one group of workers, they're all doing the same thing. They are all, let's say, welding a particular type of metal with a particular type of welding gun with a particular type of solder material. And so their exposures are going to be very similar, not identical, and we'll come to why it's not identical in a bit. But they're similar enough that we can categorize or put them in one category or one similar exposure group or SEG. On a neighboring bench, you will have another group of workers who are also doing welding, but on a different metal with a different solder material. And so they would be considered a different SEG because they are potentially exposed to a different set of compounds. And maybe in a neighboring room, you have people not welding, but mixing chemicals. So they would be yet a third different similar exposure group. And so the job of the industrial hygienist is to, based on his or her knowledge of the workplace practices and controls and tasks and contaminant properties, create these similar exposure groups. Once that is done, the job is to determine the exposure profile of each similar exposure group or SEG. And by that I mean, and this is sort of the focus of the course, determining the exposure profile means understanding the exposure distribution of workers in that group, in that SEG. And so we need to understand the quantitative probabilistic exposure distribution. We need to be able to understand the statistics relating to it and what are the measures of central tendencies and standard deviation of the exposure profile. So all of those things come under this bullet, determine the exposure profile of an SEG. The next bullet is compare the results of this with the occupational exposure limit, or the OEL. And so we'll be talking about which particular statistic relating to the exposure distribution we need to compare to the exposure limit. Which percentile, for example, or is it the arithmetic mean or some median or particular percentile that we are interested in? And on the basis of that comparison, finally, the industrial hygienist or risk manager decides whether the exposure is acceptable, unacceptable, or uncertain. Framework for occupational exposure assessment. Again, the role of the industrial hygienist, who is also sometimes called an occupational hygienist, they are interchangeable terms, is four things. The first one is to anticipate workplace hazards, recognize them when he or she sees them, and then evaluate them quantitatively, and then last, control those health hazards so that the workers under his or her care are safe from these workplace hazards. In this course, we'll be looking only at the third bullet, evaluation. So how can the exposure assessor evaluate the exposures and do the comparison with the exposure limit and make a decision? So it's these three things. I'm not going to be talking about how a particular hazard is evaluated. So we'll not be talking about measurement techniques for, say, exposure to xylene or a particular chemical or an airborne particle. So those are in other courses. So we will assume that there is a measurement process that has generated the numbers, the measurement values that we'll be looking at in this course. We'll be looking at how to compare those numbers and the distributions resulting from those numbers with an exposure limit. And we'll say, okay, what needs to happen? Meaning, what kind of an exposure control measure needs to be implemented, or that an exposure control measure needs to be implemented or not. But we'll not be talking about the different technological options available for implementing those controls. So it's, again, like I said, only the third bullet, evaluation. Now we'll get into a formal definition of what we mean when we use the word exposure. So I'm going to just read it out first. Exposure is the intensity, and in our context, in airborne exposures or any other kind of exposure in the workplace, we are talking about the concentration of a particular contaminant. And in this case, we are looking at air contaminants. So it's the concentration of the air pollutant at the interface between the environment and the human being. And in this case, since we are looking at the air pollutants, the interface is really the human lung. And so we are talking about what is the airborne concentration that the human lung experiences, or the human respiratory tract experiences. And it is for a specific contaminant, whether it's a gas or a vapor, or whether it's an airborne particulate, whether it's a biological aerosol. So anything airborne is being captured by this definition. And the other important part is it needs to be over a specific time interval that has biological relevance. And we'll talk more about this, but very briefly, some contaminants cause their adverse health effects right away. So if you are exposed to a high enough concentration of hydrogen sulfide, you could have adverse effects like within a matter of minutes. And so we are therefore interested in the exposures over a time interval of minutes or at most an hour or a couple of hours. But if the health outcome that you're interested in protecting your workers from is coal workers' pneumoconiosis, coal miners get this disease, pneumoconiosis, after working in coal mines for a few years, decades. Same thing if you are a rock quarry worker and you are splitting rock, then you might get silicosis, but only after exposure over a period of decades. So there you are not really interested in the minute-to-minute variability of exposure, but rather you are interested in the annual variability or even decade-long variability in the exposure. And so that's what I mean. So the exposure is the intensity, the airborne concentration of silica, in the case of the rock quarry workers, that the miner is breathing over a period of many years. And in the other case where you are interested in the exposure of hydrogen sulfide or the exposure to hydrogen sulfide, there you are interested in a time interval of minutes because that's the biologically relevant time interval. Let us now continue with our discussion of various definitions that are going to be used in this course. Human beings can be exposed to contaminants via a variety of routes. The three main ones are inhalation, so breathing it, ingestion, eating it, and dermal contact, I mean coming in contact with your skin. And of these three, we are focusing on inhalation exposures in this course. First of all, only as an example, the techniques can be, and the statistics can be applied to any type of exposure, dermal or ingestion. But the respiratory tract offers the greatest amount of contact between the human body and the environment. Therefore, it seems fitting that that would be the example I choose. And just as a sort of a tidbit, if we take out the human lung and sort of stretch it out on a surface, it has a surface area roughly equivalent to that of a tennis court, so about 100 square meters. So you can see that's like a pretty large amount of our body that is exposed to the environment. In contrast, if we look at dermal exposures, our entire body, in the worst case, let's say we took off all our clothes and we're completely exposed to the environment, our body offers maybe 1.5 to 2 square meters of exposure to the environment. So it's much, much less, a couple of orders of magnitude. And of course, we are not completely naked all the time. We are actually just exposing our face and maybe our hands to the environment in most cases. So the dermal exposure is really much smaller compared to the inhalation exposure tract. In this slide titled Exposure, there are a couple of points I want to make. The first thing is very important, and it is to draw a distinction between measuring concentrations of pollutants in the air and measuring human exposures to those concentrations. So if there is air concentration of benzene in some room that nobody ever enters, then it is irrelevant to human health. And we are not particularly interested in that. And we would not call it an exposure. An exposure is always to a human being, at least in this course. So we are not interested in airborne concentrations where there are no human beings. So it's only when a human being comes in contact with airborne contaminants that we call it an exposure. Otherwise, it is not an exposure. The second thing, this is an important concept, is that most modern workplaces, it's not just one thing happening in a particular place. There are a variety of processes occurring within the same roof, sometimes in the same room. So the workers, even though at any one time they may be doing only one task, they are constantly exposed to a variety of contaminants from neighboring processes over in the next bench or the next room. But each process has its own microenvironment. So if you can sort of think of me working at a bench and you can imagine a small umbrella of air surrounding me as I'm mixing two chemicals, I'm in a particular microenvironment that is related to the chemicals I'm working with. But you, in a separate room, but in the same workplace, you have your own sort of umbrella and you have your own microenvironment. And so while we can calculate an average concentration of the workplace or average concentration in the room, that is different than what I am exposed to and what you are exposed to. So this is a very important idea of the microenvironment because my personal exposure is to my microenvironment and not to the average workplace environment. So that's one thing to keep in mind. As this idea of microenvironment suggests, there is a lot of spatial variability or inhomogeneity in the workplace. So the concentrations of contaminants are not uniform in the entire workplace. They are higher in one location, lower in another, and so there are regions of high and low concentration that are not entirely sort of known beforehand. And we need to really understand the movement of air, the movement of the workers, and also, of course, where the contaminant generation sources are. And of course, there's temporal variability, meaning that concentrations change with time. And it could be a matter of within each work shift, the concentrations go up and down, but also they change over season. So in the winter months, the workplace might have its doors and windows more closed compared to the summer months when they are open. Now we can come to the concept of a breathing zone. And this is similar to the idea of the microenvironment, but it's more focused. So at every point in time, the concentration of the air being breathed in by the worker may be different from the average workplace concentration. And this is especially true for particles, but certainly also true for gases and vapors. But for gases and vapors, the microenvironment concentration is a closer approximation to the concentration of the air being breathed in by the worker. So a breathing zone is defined as an imaginary envelope of air surrounding the worker's head from which the worker is breathing the air. And so if I'm standing and I stretch both my arms to my side, you can imagine a hemisphere of air with my two arms forming the diameter of the hemisphere. And this hemisphere is covering my head. And so that basically is the breathing zone. That is my breathing zone. And so it is the concentration of the air pollutant in this hemisphere that the worker is exposed to or I'm exposed to. If you looked at a non-occupational setting, the same concept applies where, let's say, a person cooking in their home is exposed to the smoke from whatever stove they are using, for example. So the idea is applicable to occupational as well as non-occupational settings. Let's continue on further. Now we are going to get a little bit more precise and quantitative, and we're going to put a formal definition of an exposure. So we have in this first integral equation the concentration denoted by C, and C is a function of time t. And so if you remember the definition of exposure, it is the concentration of a particular contaminant over a specific time interval. And so that time interval is, in this definition, 0 to capital T. So the time interval T is the one that we have decided has biological relevance. And so we are going to integrate the time varying concentration in the breathing zone of the worker over this time 0 to capital T. And that is defined as the exposure. And so if our units of the concentration are milligrams per cubic meter, so milligrams of contaminant per cubic meter of air, then the units of exposure are concentration time, or in this example, milligrams per cubic meter hour. We don't necessarily have to do an integral every time. So if we know the average concentration over specific time intervals, then we can have the discrete version of the integral where we say that the exposure is the concentration over a particular time interval times the length of the time interval, and you sum it over n different time intervals. So what this formula is saying is CI, that's the concentration in the ith time interval, times the TI, which is the length of the ith time interval, and you sum it over n different time intervals. And the total time t is the sum of each of the individual time intervals. So as you can see, both the integral and the discrete form, the summation, refer to concentration being summed over a time interval. However, one additional thing that we do is we don't express exposure in the way I showed you in the previous slide. We actually express it in terms of a time-weighted average concentration, meaning we divide that integral by the total time, so that the exposure is in terms of not milligrams per cubic meter hour, but just milligrams per cubic meter, since we are now dividing out the whole integral by the total time. So in the top equation, we can see the exposure is the integral of the concentration over the time interval 0 to t divided by t. And the same thing is true for the discrete form of the equation, where we take the summation of Ci times Ti over the n time intervals, and you divide it by the sum of the n time intervals. And if we can further simplify this equation, we see that the lowercase ti divided by capital T is the fraction of time spent by the worker in the ith microenvironment. And so the exposure becomes a summation of the concentration in the ith microenvironment times the fraction of time spent by the worker in that microenvironment summed over all the microenvironments. I want to illustrate the equations that we discussed graphically. And so this shows the time scales of exposure. So what I'm showing is sort of a hypothetical variation of concentration with respect to time. So the x-axis is time, and the y-axis is the concentration. And you can see that there are peaks and valleys in this variation. Now, if you are interested in a disease caused by chronic exposure, long-term exposures, then you are really looking at the long-term time-weighted average. So if we take this time t0 to t0 plus t along the y-axis, and we consider that the time period over one work shift, for a chronic exposure, we really don't need to know the minute-to-minute or hour-to-hour variability. We really need to know what is the average for that day. Or sometimes we don't even need to know the average for that day. We need to know the average over a year or even like 5 years. So that's what we really are interested in. But if we are interested in an acute effect, then we really are interested in the minute-to-minute variability in the exposures. We are interested in the peak exposures because that might have something to do with your adverse effect. The other thing I wanted to point out was that the integral of the concentration gives you the exposure. And so the integral is the area under the curve. So if we are looking at the time interval lowercase t0 to t0 plus capital T, then the area under the curve is shown by the shading, and that is the integral value. Okay? But we can also replace it. The area shaded under the curve is equal to the area bounded by the rectangle, and the width of the rectangle is capital T, so from t0 to t0 plus t. And on the vertical axis, the height of that rectangle is C average. So the area of that rectangle is essentially the same as the area of the shaded area under the curve. And so that is what we mean by an exposure. We are essentially taking an average over some time period. And that average is representative of all the variations, and it is basically giving you the same area under the curve as the actual time variation.